As usual, with your special students, you probably already know how to do these definite integrals, so carry on. For method students, I believe integration wasn't a big thing last year, so you're probably still trying to work through anti-deriving, which is the opposite of derivatives. And then now, definite integrals is essentially finding the value after you anti-derive. Kind of like differentiation. You get the derivative, and then you sub in a point to find the gradient at a particular point. Well, then this is like your version of finding the area between two intervals. So that relies on a formula, which you're going to fill in here. For those of the first time seeing this, this is called definite integrals. Definite integrals is another way of saying once you antiderive, but between two certain points, you're essentially finding the area under a curve between those 2 points. So the formula is, if you're antideriving a function between a and b, so a is the smaller value, b is the larger value, then the area can be calculated as, and we write capital F, which I'll explain later, of b subtract capital F of a. What's capital F? Capital F is after you're able to antiderive f of x dx, which is indefinite integrals, what we did last week. So using the rules, figuring out which rules you have, applying the correct formula, you then get a function. Whatever that function is, we call it capital F of x. Why? Because we usually think of it as capital F of x. If you then derive it, you get the small x. So that's kind of like deriving. Working backwards is anti-deriving. That's the idea. Okay. This here is actually a really big theorem in terms of like a big breakthrough. But for your case, we're just going to practice using the rule. Okay. But usually that's meant to be gone through and to see why it's such a special rule. It's called the fundamental theorem of calculus. So if you're interested in finding the origins and proof to it, check out Khan Academy. That's a good one to have a look at. But otherwise, let's break it through. So when you do the antiderivative between a and b, you're essentially finding the area, calculating the area between a and b for that function, and it's the area under the curve bounded by the x-axis. And this is known as the definite integral. It means you're going to get an answer. You're not going to have a plus c. You're going to get a value, and that value represents the area. Okay. However, one of the things you've got to be careful of when you're finding this between a and b, you're actually finding the net area. And what I mean by net area is if you look at this picture on the side, that's a straight line. This equation is y equals x plus 1. Okay, so that's your y-intercept at 1, x-intercept at -1. That's your y equals x plus 1 line, right? If I told you to find the antiderivative of x plus 1 dx, remember you always have to have dx, between -2 all the way to 2, so -2 to 2, it will find the area under the curve, under the graph, and the x-axis. So you can see you got A2 and you got A1. These two, it will find the area of these two together. The problem is that one area is above the x-axis, so that's considered positive area. The other one is a negative area. Okay? So when you add these two areas together, you're going to get less than what it would actually be. That's why it's called a net. It means that you can potentially do the antiderivative of a graph that is, say, y equals x. So it's symmetrical. And I say, find the area between -1 and 1. So we know that in a y equals x, this would be a triangle of left by 1, down by 1. This will be to the right by 1, and then up by 1. The area for these two are going to be the same. So A1 and A2 are the same. If you type that on your calculator, find the antiderivative of -1 to 1 of x dx. That will equal to 0. But we know that it can't be equal to 0 because clearly we have two areas there. Okay, we've got two areas that should add up. So you got to be careful with the question. If they ask for the absolute area, if they're actually asking for the value of the total area, then you don't calculate the net. You actually have to calculate them separately. Okay, you have to calculate them separately. If you know the ones that are below the x-axis that's negative, you've got to convert it to positive, and then you add them all together. Okay, so in this case, if we were to quickly work out the area of a triangle, half base times height. This one would have been, what, half times 1 times 1. We've got an area of half. That one would have been area of half as well, but it's negative half. If you typed on your calculator, would have done half, take away half, and gave you a net area of 0. But if you actually wanted to find the total area should have been A1 plus A2 should actually equal to half plus half, which is 1. So be careful if they're asking for net area, or sometimes they call it sign area, or they're talking about total area. If the question says total area, this is what you're meant to do. If they don't care, then you pretty much can type on any CAS and get a net area. So most times they'll probably get you to work out total area. Okay? All right. So that was the main thing, just to be careful when you're doing the questions. But here are some properties, especially for those who are new to integration for methods. Here we go. So we've got f of x is equal to, now what happens if you find the area where the interval is exactly the smallest interval to the maximum interval is still the same? So in the example that I gave to you before, what if it was a straight line? And I said, find the area at 1 and 1. So it's a single point. So it just happens to be a line. In that case, the area is 0. Okay, you cannot find the area of a single point. You can find the area of an interval, but not a single point. And that's where it'll lend well into probability next term, continuous versus discrete. It's based on that idea. Discrete, you can count, so you can find the probability, but in continuous, there are infinite. So that's why, since we can't do it, we've got to do it interval. And that's where continuous probability involves integration. So you've got to learn integration first, is what I'm saying. Next one, let's look at the next property. If you have a constant that's a scalar multiplication to a function, well then we know we can actually take out k and write the antiderivative, so k times a to b of f of x dx. Okay, so you can take out a constant that's multiplying. If you have integration of two different functions added, which hopefully you picked up from our last session, you can antiderive them separately as well. So it means definite integral is the same. You can also antiderive them f of x dx between a and b plus antiderivative of a to b of g of x dx. If you have an a to b interval, you can also split up the interval as well. It doesn't always have to be just from start to finish. So it means you could also do it, say from a to b was like this, and this is your straight line. You don't have to find the area from start to finish. You can actually split it up. You could also do it from, say, a to c. If you made up a c value, find out the area of a to c. So say a to c of f of x, and then do from c to b for f of x dx. Notice I forgot dx here as well. So just make sure your notation should always have dx. If you don't have delta x, then it will be considered incorrect. And you can add those two together separately, and it works as well. So it means you can antiderive, find the area between a and c, and then area from c to b, add them together. It is the same thing as finding from a to b. Okay. Next one, and the final one. This one is a nice property that you will find in the exams they often use, that if you can do from a to b, okay, so from a to b, providing a is smaller than b. Remember, the smaller interval or integer is always, so not integer, but value is on the bottom, and on the top is your maximum value. If you swap the intervals around, so say the larger value is b on the bottom and a is on the top, that's essentially the same thing as flipping, find the area below the x-axis. Okay, so This one you can do f of x dx. So that's why there's that negative. Okay. And that's a genuinely a nice popular property to know, especially in multiple choice questions. So let's do an example now. So those are our properties. We've got an idea. Here's your fundamental theory of calculus to find your area value. Let's practice indefinite integral and then how to apply it into definite integrals. Here we go. Let's do a simple one. I'm going to do example 1a just to get those who are new to this to start off with. So first thing, it's still the same thing. You've got antiderive x squared dx. Here's your rule again for those who are learning. Antiderivative of ax to the power of n dx. This is what we learned last week. It is the same thing as saying x to the power of n plus 1. So remember, you've got the n plus 1 over n plus 1. Remember, it's the reverse of that. Okay, and then don't forget the extra plus c. The a, you can think of it as a contributing, it's a k value, so you can actually put it to the front. It's kind of like that. So you got add by 1 and then divided by n plus 1. Okay, so we have to antiderive this. Let's see if you remember or at least can practice doing this. So 1 to 2 is the interval. So I'm going to put 1 to 2 to remind it's between 1 and 2. Let's antiderive x squared. What would the antiderivative of x squared be? Can I have... Let's go, Krish. No, not the derivative of x squared. Yeah. Derivative of x squared is 2x. Now we're antideriving. Going backwards. So derivative of something gives you x squared. That's all right. Someone else? Let's go with... Yes, Sumar? X to the 3 over 3. So using the rule, we know that n is 2. So going backwards, it'll be 2 plus 1. So you get x to the power of 2 plus 1, which is 3. But remember, the power rule, usually you times by the n. So in this case, you're now going to divide by n. So in our case here, it would be divided by 3. Okay, that's to cancel. Usually, if I found the derivative of x cubed, it would have been 3x squared. So the 3's cancel out. That's what the 3 in the front is for. Okay, so you got x cubed on 3. Very good. So that's the only part that's called the indefinite integral. Now you notice there's a little detail here that I may not have mentioned. Indefinite integral last week, I said that you should put a plus c. You'll find that you actually don't need the plus c when you do definite integrals because they cancel out. So I'm going to put it in just so you can see how they cancel out. But in the future, don't put the plus c inside because there's no point. So if you found the antiderivative, you get the plus c. Now we apply the rule, the fundamental theory of calculus rule. We said to find the area, it's f of b subtract f of a. This is my capital F function now. Okay, so I got capital F is x cubed on 3 plus c. That's indefinite integral. To do definite integral, we're now applying the intervals 1 and 2. So how do I apply it? Here we go. F of b, b is the larger value. It's the top number. So f of b would be sub 2 in. I want to sub the number 2 into the function. And I will get now f of 2, which is the same thing as saying 2 cubed over 3 minus f of 1, because that's my lower interval, so f of 1, so minus 1 cubed on 3. Okay, now if you're wondering where's the plus c, so if I put the plus c, can you see, by putting the plus c in, see when you said minus f of 1, if I put the plus c in, the minus and the positive will end up being a negative c. So whatever this is, these two are always going to cancel out. That's why we don't put the plus c anymore. Okay, the plus c's always cancel out. So because of that, you technically just end up with 2 cubed, which is 8, on 3 minus 1/3, And you can see here that gives you 7 on 3, or 2 1/3. There we go, and that's the answer. That gives you the area. So they're saying that the area between 1 to 2 of x squared is 2 1/3, or 7/3. I want to show you on a CAS. Here we go. If you grab out your CAS, there's a shortcut function. You can go to menu, and then calculus, and then integral. You can do it that way. So menu 4-3. Or on your CAS calculator, if you press shift and press the plus button. Shift plus is antiderivative. Okay, so if I do shift plus, I get the antiderivative template. And I'm going from 1 to 2 of x squared, whoops, delta x. Let me do it again, delta x. And that's how you can see you get your 7 on 3, which we just did by hand. Okay, but the shorthand, shift plus works. Shift minus is derivative, if you didn't know that. Shift minus derivative, and shift plus is antiderive. Okay? All right. So that is, I think in year 11 last year, we gave a sort of a start of intro to this. So that's a bit of a revision from last year, and that's what you're practicing last week. What you're practicing this week again is now applying f of b minus f of a. Okay? So what's your challenge in this exercise is to remember how to apply antiderivatives and then use f of b minus f of a. Okay, so let's try the next one. This one feels tricky. Hopefully this will revise last week's stuff again. So I just did a power rule. We did the antiderivative of a power rule. Now we're going to do antiderivative of a chain rule. So this one should be, can you antiderive from 8 to 10? 2x minus 5 technically is to the power of half because you're saying square root. The question is, do you know how to antiderive this? Which rule did I give to you last week that allows you to do that problem? So then that's where you go through the notes, look at how to antiderive, and hopefully at some point you'll learn all the rules without using a CAS. But here we go. Since some of us are new to antiderivatives, I'm just going to write the rule again. So antiderivative of ax plus b to the power of r, if r, as long as r is not equal to -1, so it doesn't end up in that log thing that I was talking about last week. And the rule says, since we've got the a in front of the x, remember chain rule, you would have found the derivative du dx and then times dy du. So in this case, you have to have the 1 on a at the front. It's to counteract that derivative that you would have done inside. Times by, and don't forget, you're going to use the power rule again. So power is r, so it'll be 1 on r plus 1 times ax plus b to the power of r plus 1. Okay? So instead of trying to show you what we did before. So before was just x to the power of n, and it was n plus 1 over n plus 1. In this case, it's still the same, except I've got an extra a at the front. Okay, so it looks scary, but it's not. So we apply the same rule. Let's see. Let's go with someone else this time. Let's go with some methods students only. Who does methods only? Arian, that's right. Arian, you do methods only. So I've given you the rule just over there. And you've got your function, 2x minus 5 to the power of half. So r is equal to half, our a is equal to 2, and b is equal to -5. Let's do some antiderivative, shall we? What is the antiderivative of 2x minus 5 to the power of half? You've given me the first value. Take your time. So this is my a. This is my rule. 1 over 2. Very good. So we start with 1 on 2. Next one is where most students tend to make a mistake on the exam in terms of the average student. So the average student would normally make the mistake. They'll go, okay, half. Good, no problems. Next one. 1 over r plus 1. Now r is a half. What's a half plus 1? Let's go with Alicia. What's half plus 1? Very good. So half plus 1 is 3 on 2. And this is where students get stumped in the exam. That's why they used to use this quite a bit. So if you look at, I think 2013 to maybe 2015 or 16, that was quite alternating. They do this one versus the one that's log, and they'll just alternate between the two. So a lot of students get stumped here. 1/3/2 is the same thing as saying 1 divided by 3/2. And back in primary school at year 8, they call this KFC method. Keep the first, flip the second fraction, and change the sign. That essentially is just saying 1 times 2/3, because you're flipping the 3/2. So essentially 1/3/2, if you simplify that, that's the same thing as writing half times 2/3. And that seems to stump a lot of students, just the fraction skills. Next bit. So I've just gone through 1 on A, so 1/2, 1/r plus 1, which we just did. And now we've got ax plus b to the power of r plus 1, which is pretty easy there. We'd write then 2x minus 5 to the power of half plus 1, which is 3/2. Putting them both together, 2x minus 5 to the power of 3/2, we can already see 2 half times 2/3, these 2's will cancel out. So your antiderivative so far should be 1/3 times 2x minus 5 all the power of 3/2. That bit there was the antiderivative last week. So what I just did there, this very first 2 lines, that's antiderivative. We're doing definite integrals. We've got 8 to 10. So I use square brackets. That's the notation that we use. And we put in our intervals from 8 to 10. Using fundamental theorem of calculus, it means you're going to sub in 10 minus sub in 8. So here we go. You should then have 2 times 10 minus 5 all to the power of 3/2 all over 3. Take away 2 times 8, take away 5 to the power of 3/2 all out of 3. And yes, that can come up in exam 1. You can see why they used it quite a bit previously. It's because they're trying to see if you can work with your fractions in substitution here. Here we go, let's see. What does this give us? We got 2 times 10 is 20. 20 minus 5 is 15. So you got 15 to the power of 3/2 over 3. Take away 2 times 8, which is 16. 16 minus 5 is 11. So you got 11 to the power of 3/2 on 3. And now we can combine the denominators together. They're all out of 3. 15 to the power of 3/2. Take away 11 to the power of 3/2. Can I simplify that any further? 3 and 5. Not that I'm saying. Did I miss out on anything? No? I feel like this can be simplified. Does anyone say anything? What can I simplify? 20, take away 5, 15. You can't do 15, 3. Cast root 15. 5 and 3 doesn't work out. No. Is that what it says? That looks ugly. Let me see. Shift plus. 8 to 10. Square root. Oops. Square root. What was it again? 2 times x minus 5, I think it was. Dx. Yes, it is. Okay. Oh, it was. Oh, wait. Yeah, it was. They just read it differently. Okay. All right, cool. I guess that was a random problem I put together then. Oh well, there we go. So what you can see, that's called definite integral for those who are new to methods. It's really practicing your antiderivatives and then applying f of b minus f of a. I've got the solutions for the next ones for you to practice here. I'm going to delete this one because this is a common problem that I find in the exams that students struggle with. So I'm going to show you a visual idea so that you know how to do them when you see it in an exam. Flip over the page. 11E question 4 is in your textbook. So, in the exam, I'll do the first three so you get a vibe of it. In the exam, you could get something like this, where they might say, given that the antiderivative of h of x, which you don't know, and they don't give you h of x, but they say it's between 0 and 4, the area is 5. Okay, so I don't know what h of x is, but I just know that the area under the curve between 0 and 4 is going to equal to 5. So when they say, find then, what's the antiderivative or the area between 0 to 4 of 2 times h of x? This is where you start applying your properties. So you can see this becomes, you can write 2 at the front, 2 times 0 to 4, h of x dx. And since we know that this is equivalent to an area of 5, you can then say that equals to 2 times 5, which is 10. But I want you to try to visualize it, because when it gets a bit more tricky, and that's what they do in the exam, I want you to visualize what the problem is. See, if I drew a graph, hypothetically, h of x is a nice straight line. That's usually how I like to visualize it. 0 to 4. That area is 5. That's what you know. Okay, so I just made up that h of x is a straight line. I don't really care because it could have been a curve, and the point is this area right now is 5. So it could have been a funny curve. That area is 5. When you say 2 times h of x, you're really just doing a dilation of factor 2 from the x-axis. Because that's what you're doing. You're timesing 2 to the function. So you're really just dilating this by a factor of 2 from the x-axis, which just means stretch this by 2. So logically, that makes sense why you do 5 times 2, and it doubles in itself, and you get area of 10. If you try to visualize for the next one, even without doing the algebra, you should be able to get the answer logically. So here we go. Here's h of x, 0 to 4. Here's your area. You know the area is 5. Now what happens if we say plus 3? What type of transformation is a plus 3? What type of transformation is a plus 3? Vertical. It's essentially just saying shift the graph up by 3. Now if you shift up the graph, this is what it's going to look like. So imagine I take that rectangle of area 5 and I shift it. So I'm going to draw it again. I'm going to make a nice rectangle here. If I shift this graph up by 3, so I shifted it up by 3, plus 3. This area is still 5, this one here. But what I've created is another area of 3 units up, but the length is still 0 to 4. So I'm really just adding on another piece of area, because if I said, what's the area under this curve now? Isn't it just 3 times 4 gives me, so that's your plus 3. I've shifted the graph up by 3. So really, the answer should just be 17 if I looked at that. But you can also apply our properties, and we could have split it up and done 0 to 4 of h of x plus antiderivative 0 to 4 of 3 delta x. And you would have said, oh yeah, this equals to 5, because we already know by the identification, plus, and then you do your indefinite integral. Now let's see if you remember, what's the antiderivative of 3 again? Let's go with, who's another method students? I think it was Adonis. Adonis, do you do special? No? What's the antiderivative of 3? 3x, very good. So we get then 3x here between 0 and 4. Use fundamental theorem of calculus. Apply 4. So 3 times 4 is 12. Take away 0. And you can see there, we end up with the same result. 5 plus 12 gives you 17. So you can do it that way. But I like you to try to, especially in the exam when they start moving it around, they'll apply all different types of transformation. They'll do reflections, they'll do dilations. And the tricky one is the one that's dilation from the y-axis, because that changes the domain. And that's why they have to change the intervals specifically to fit whatever transformation they say. But it looks scary. So the easy ones are vertical translations and vertical dilations. It's when you work with horizontal dilations that the picture might help. Okay? And this one, obviously, we swapped the intervals around. 4 is bigger than 0. So that's pretty much using the property knowing that 0 to 4, negative h of x dx, that will give you area of negative 5. Okay? But that's a really nice sort of idea. I'm hoping you to try to use your transformations. And I like to use a horizontal line just to visualize what's happening. I mean, you could do a curve. It really doesn't matter. But that's one of the ways I do it to visualize what's happening. Okay? But I've left those two there if you want to visualize or try just doing the antiderivative. That's part of your textbook. But here and there, you'll find that type of question in your multiple choice section for exam 2. All right. All right, let's flip over. And let's do a final question. This one's tricky. Final question. We're now doing signed area versus total area. So I said to you before that when you're finding the antiderivative, it is the net area. Also, the definite integral is the net area. So here we know that area under the x-axis, so below the x-axis from A to B, negative of A to B is the same thing as finding, sorry, that should have been B to A. That should have been B to A there. That should have been B to A. So antiderive f of x from B to A is the same thing as finding the area of negative of A to B f of x. Okay. When calculating the area of different regions, split them, especially if you have like negative region versus a positive region, split them up in terms of interval and then add them together. So here's an example. In the figure, the graph of y squared equals to 9 times 1 minus x. Looks like this. I'm going to rub this out so you can see. So you're given a diagram. I'm just going to explain it to you and then I'll explain the solutions to you. But I want you to have a go first, thinking about how would you problem solve it. So this is your curve. That's your y squared equals to 9 times 1 minus x. They first tell you to find coordinates a and b, so you can do a bit of problem solving to find a and b, x-intercept, y-intercept. But the real question is asking in part B, find the exact area of shaded region by evaluating 0 to b. So 0 to b, 1 minus y squared on 9. So where did they get this from? They just rearrange the equation. They just rearrange the equation to get there. So I want you to have a look at A first. I've done the answers for A, but I want you to try find A first and then see if you can then figure out how would you do part B. Then I'll show you my answers and then I'll explain through it. And that's your last example for today. Okay, but you can see what today's lesson is about. It's area under the curve using fundamental theorem of calculus. There are some properties that you got to learn to apply, and then sine versus total. Okay, so for students who aren't doing special, this would be quite a bit to take in. So that's what your practice is over the holidays, is to make sure you've learnt how to antiderive and work between them. Okay, I'm going to pause the video. All right, let's continue. So I left you off with example 2, a question A. Whoops. First one was to find coordinates A and B. If you didn't, have a go, because it looks scary. It was just finding x-intercept, y-intercept. Let y equal to 0. You can clearly see that x will then equal to 1. So that one point there is at 1, 0. Then for the y values, let x equal to 0, and you end up with plus or minus 3. So this is your graph. You've got plus or minus 3, and you've got 1 here. What is the problem if you said, let's just find this area? Is because if you just said, this is the curve y squared in terms of x there. If you then said antiderivative, so if I just did square root both sides, y is equal to the root of 9 minus x delta x there, which you can do. There's a plus and minus there. You're working between, you want 0 to 1 of root 9 minus x delta x. That finds the area. Remember, the key part here is the delta x. It's saying that the strip of rectangles, to find the area, you're doing this. You're doing one rectangle plus a rectangle plus a rectangle, and it's delta x each time. Change in x. You're adding all these rectangles vertically from 0 to 1. That's what you're doing. That's what that's saying. Versus what they've done over here, they're asking you to do from 0 to b, 1 minus y squared or 9 looks scary. But all they're actually asking you to do, and if you look at the algebra that I've done, they've just rearranged it, expand the brackets, rearranged the y to make x the subject and what in terms of y. So if I moved everything across, you can see x equals to 1 minus y squared or 9. Why did they do this? Because what they're saying now is find the integration or the antiderivative, 0. So starting from this point, 0, delta y, because it's in terms of y. So you're now making rectangles not vertically, but now along this line instead. So you're starting from here, from each y value, you're making horizontal rectangles. So this is your delta y, and essentially you're adding all of this, and it should be the same area, but between 0 and 3. Yep.
Easier to just like integrate from 0 to 1 and multiply by 2.
Yes. But the question was in the textbook, I think it was just to get students to understand that you can switch it around and do it by delta y. Yeah. So the area, well, if you times by 2, you get the total area, but they only want the top half.
Oh, yes.
Yeah. So in this case, yeah, they just wanted you to understand what is that b value, and when students look at that, they're like, oh, I don't know where that came from. But the delta y was the hint. It's saying that this is in terms of x, change the function to terms of y, integrate with delta y. And that's what essentially just basically means, that you are now doing horizontal strips, delta y, and then you do it from here. So we know then the top value has to be then 0 to 3. Okay? And then same thing. So the area, once you do the antiderivative of that, same thing, you do fundamental theorem, sub 3, sub minus 0, and you'll get exactly the same answer. But why is that skill important? This ability to know that you can do horizontal strips links to the next question, but I only would encourage you to do that once your definite integrals was good. Okay, so if your definite integrals from the exercise was better, then you can practice doing this typical exam question where you have to solve through horizontal strips to get there. Okay, so what you're practicing at the moment is doing vertical strips, but know that you can also do horizontal strips, and sometimes horizontal strips can make your problem easier. Okay? But I'm going to stop there. That's as much as it should be for those who are new to integration. Keep practicing your antiderivatives, and then apply definite integrals. Next session is going to be area between curves.